Hello guys, it's me again, Mr. Lau. So today we will go through assignment 6. Okay, so for the first question, write down the characteristic gas equation and define each term using the equation and state their units. Okay, so as mentioned in the lecture, there's two forms. One is PV equals to mRT and the other one is PV is equals to N R naught T. Okay, so for both cases, P will be pressure. Okay, and for pressure this will be in Newton per meter square, or it can be in Pascal. Okay, and your V will be your volume. In this case, volume is meter cube. Okay, so on the left hand side, M is in kg. Okay, and on the right hand side, N is in moles. Okay, so of course when you use this equation is when you are given the mass in kg, and when you use this equation given the quantity of the gas in terms of mole. Okay, so another difference is that the R is different. This R is the gas constant, okay, while this R naught, okay, is a universal gas constant. Universal. Okay, so the R here and the R naught is different. So R naught is standard, which is 8314. Okay, and the units is in terms of joule per kg mole Kelvin. Okay, so 8314 joule per kg mole Kelvin, while R, okay, is just simply joule per kg Kelvin. Okay, and of course the last term is T, which is temperature, and this must be in Kelvin. Alright, so that's all, okay, for the first question. For the second question, a rigid vessel of 0.7 meter cube containing a perfect gas at pressure of 2.5 bar and a temperature of 30 degrees Celsius. Determine the mass of the perfect gas. Okay, so in this case, since they want the mass, okay, so you have to use PV is equal to mRT. Okay, so put in the values. Pressure is 2.5 bar, change it to Pascal, which is 2.5 times 10 to the power 5. Volume 0.7. Mass is unknown. Okay, R is 287. Okay, take note, given is 0.287, but this is kilojoule per kg Kelvin, so you must change the kilo to joule. Alright, and your T is 30 degree plus 273, again changing it to Kelvin. So with that, your mass, okay, you can calculate it to be 2.0124 kg, thereabouts. Okay, that's it for question 2. Question 3. A rigid vessel of 0.3 meter cube containing 10 kg of nitrogen at a temperature of 32 degrees Celsius. Calculate the pressure of the nitrogen in the vessel. Okay, so we are given R naught and the molecular weight of the nitrogen is 28. Okay, so again we have to use PV equals to mRT, but R is not given, instead R naught is given. So the relationship between R and R naught is R equals to R naught over M. Okay, whereby R naught is the universal gas constant, M is the so-called molecular mass. Okay, so this will be 8314, okay, divided by 28. Okay, so this will be your R value. So with that, we can use PV equals to mRT. Okay, so P is an unknown, so we leave it. V is 0.3. M is 10 kg. R is 8314 over 28. Okay, and your T is 32 plus 273. Alright, so with that, do the calculation and you should be able to get your pressure to be 30.18 times 10 to the power 5 Newton per meter square. So if you convert, this will be 30 0.18 bar. Alright, that's it for question 3. Okay, next, question 4. 0.135 kg of a certain perfect gas occupies a volume of 0.015 meter cube at a pressure of 8 bar and temperature of 27. Determine the molecular weight of the gas. So R0 is given by 8.314. Okay, so since you are given in terms of kg, we shall use PV equals to MRT again. So we are asked to find the molecular weight. Okay, so what we can do here, okay, is we can replace R by R0 over big M. Okay, because we know R is equal to R0 over big M. So this M is our unknown. Okay, so we can sub the values in. 8 times 10 to the power of 5 times the volume, which is 0.015, mass 0.135, R0 8314 over my M, and T, which is 27 plus 273. Okay, so from this equation we can calculate our M, which will give us 28. Okay, so in this case it will give it 28 kg mole. Okay, this is so called the units lah. So therefore the molecular weight is 28. Okay, molecular weight is, there's no units. Okay, so for question 5, in a closed system, a certain perfect gas of volume 0.1 meter cube with an initial pressure of 1.02 bar and a temperature of 40 degrees Celsius is compressed to a pressure of 6.5 bar and a temperature of 115. Determine the final volume of the gas. So in this case, we have a process. Okay, the process goes from stage 1 to stage 2. Alright, so for stage 1, okay, what are the values given? We are given P1 to be 1.02 times 10 to the power of 5. We are given V1, which is 0.1. We are also given T1 to be 40 plus 273. Okay, for the final stage, this will be P2, which will have 6.5. V2, which is our unknown. T2, which is our 115 plus 273. Alright, so this is a process 1 to 2. So in this process, we are concerned with these 6 values. So one of these is unknown. Therefore, we can use our perfect gas equation. P1 V1 over T1 is equal to P2 V2 over T2. Okay, and sub in the values. Okay, sub in the values. So P1 is 1.02 times 10 to the power of 5 times V1, which is 0.1 over T1, which is 40 plus 273, which is equals to P2 6.5 times 10 to the power of 5 times V2, which is my unknown, over 115 plus 273. Okay, so from here, press the calculator and you will get our V2 to be 0.01945 meter cube. Okay, that's it for question 5. Next, question 6. A rigid vessel containing a perfect gas has an initial pressure of 2 bar and a temperature of 28 degrees Celsius. It's heated to a pressure of 2.6 bar. Determine the final temperature of the gas. So same thing, a process. Okay, so we have a P1, which is 2 times 10 to the power of 5. Okay, and we have a T1 is equal to 28 plus 273. Okay, P2 2.6 times 10 to the power of 5. T2, which is our unknown. So you realize that V is not given, but the clue here is this is a rigid vessel. So for a rigid vessel, the volume doesn't change, meaning to say V1 must be equals to V2. So writing our equation again, P1 V1 over T1 is equals to P2 V2 over T2. So without even hesitating, we can cancel away V1 and V2. So sub in the rest of the values. And we can get our T2 in terms of Kelvin, 391.3 Kelvin. Okay, that's it for question number 6. Next, for question 7. Okay, we have a closed system, a certain perfect gas having an initial pressure, volume and temperature of 1.4 bar, 0.1 meter cube and 25 degrees Celsius is compressed to a final pressure of 7 bar and 60 degrees Celsius. Take R to be 0.29. Determine the mass of the perfect gas. Okay, so to determine the mass of the perfect gas, we can use all the initial values. Okay, and in this case the initial values is 1.4 bar, 0.1 meter cube and 25 degrees Celsius, so we can plug it into PV is equals to mRT. So 1.4 times 10 to the power 5, 0.1 m, R is 290, okay, and T is 25 plus 273. Okay, take note in using this equation, if all the values are from 1, okay, it must all be from 1. Okay, you cannot just interswap or interswitch the values. Okay, all this must be from the initial stage. Alright, so from here you can calculate your mass to be 0.162 kg. Next, to find out the final volume, again, because this is a process, we can use P1 V1 over T1 is equals to P2 V2 over T2. Plug in the values. P1 is 1.4 times 10 to the power 5, V1 is 0.1, T1 is 25 plus 273, P2 is 7 bar, okay, V2 is our unknown, and the final temperature is 60 degrees. So from here you can solve your volume to be this value. Alright, pretty simple. Next, for question 8. Again, we have a closed system, perfect gas, initial pressure of 3 bar, volume of this and temperature of this, expanded to 2 bar. If the temperature remains constant during the process and R is this value, determine the mass of the perfect gas. So same thing, we use PV equals to mRT, okay, and we use all the values of the initial stage. Okay, so P is 3 times 10 to the power 5, V is 0.08, okay, M is our unknown, R is 295, T is 32 plus 273. From here, M will be 0.2667 kg. B. The final volume of the perfect gas, P1 V1 over T1 is equals to P2 V2 over T2. And since, okay, the key word here is that the temperature remains constant. Okay, so T1 can cancel with T2. Plug in the remaining values. P1 is 3 times 10 to the power 5, V1 is 0.08, P2 is 2 times 10 to the power 5, V2 is our unknown, and we can solve our V2, 0.12 meter cube. Okay, can. So that's it for the last question. So as a prelude to chapter 7, okay, chapter 6 actually introduces us to perfect gas, the concept of a perfect gas. Remember, perfect gas is an idealistic theoretical gas, okay, that we use for studies. So all the equations to calculate the P, the V, the T, the U, the H are all equation based. Okay, do not take the values from the table. Okay, it's slightly different from the first part of what we learned. Okay, but later on in chapter 7 we are going to go through quite almost the same thing again, which is the constant volume, constant pressure, isothermal, polytropic and adiabatic processes for, in this case, perfect gas. Okay, Ken, thank you so much. Again, apologies for last week's video. The quality wasn't that good. Hope you can bear with me. Okay, have a good weekend ahead. Have a good rest. Bye.